Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am very happy to have Ben Proudfoot with us today. Hello, Ben.
Hi, everyone.
And Ben, what's your geolocation? Where are you at?
I have just recently started a new position, a postdoc position at the Florida Space Institute in Orlando. So I'm here in sunny Florida.
Oh, congratulations, Dr. Ben. I think that's wonderful.
Thank you.
And speaking of Florida, you do have a rocket ship over your left shoulder there. So yeah, let's talk.
I have a Saturn. They're all Lego. I have a Saturn V, and obviously a space shuttle, the
Yeah.
International Space Station, and if you can see right there,
Yes.
I have the Hubble Space Telescope.
Very cool. Well, you're certainly in the right location at this point.
Exactly.
Very cool. Very good. And Ben, what do you like to do for research?
So I mostly study TNOs, so trans-Neptunian objects, the things that orbit outside of Neptune.
Mm-hmm.
And I am most interested in understanding how binaries orbit and how they form and evolve and things like that.
That is awesome. Very cool. Very cool. And that is going to bring us to this very awesome AJ article. It is open access. It's the open access era. People go grab a copy for free. Beyond point masses. 2. Non-Keplerian shape effects are detectable in several TNO binaries. And Ben, take us away.
So to start, I will shout out my co-authors. The big one, the second author, Darren Ragazine. This paper was actually part of my doctoral dissertation, and Darren was my advisor. Cool. So big shout out to him. And you can see I also have 60-something other co-authors, almost all of them from BYU, where I did my doctorate. Cool. And those were actually undergraduate astronomy students in Darren Ragazine's solar system astronomy class. So mostly sophomores.
Wow.
So yeah, two years of sophomores contributed to this work and put in a lot of legwork, learning, what a J2 is, learning what a TNB is.
Yeah, very cool.
And so we're really excited to have them all as co-authors on the paper.
That is awesome. That is so nice of you too. That's really wonderful.
Yeah, we were excited about that.
And I suppose I should state a mild conflict of interest. I do want to call out that Darren is also a scientific editor for the Planetary Science Journal, PSJ.
Yes, he is.
All right, onwards.
So the article is mainly about TNBs. So TNBs, or trans-Neptunian binaries. Mm-hmm. Many people call them TNO binaries, but we like to abbreviate a little bit. So many TNOs are part of a binary system. So the first one was discovered in I think the late 90s or early 2000s, 1998 to WW31. And ever since then, people have kind of recognized that they're super great kind of just probes of how planetesimals in the trans-Neptunian region form, evolve, and they kind of give us a little laboratory. I put it all in my grant proposals that TNBs are the perfect little laboratories to do science.
Very good.
So there have been something like 100 to 150 discovered, and of those, about 40 to 50 have been characterized. And when I say characterized, what I mean is we have their orbits figured out. So we can measure their mass from that. And so of those characterized TNBs, this paper mainly focuses on that. So with TNB studies, since the beginning, in the early 2000s, everybody has just used Keplerian orbit models. So 1 over r squared gravity, just the standard of what we would expect. And they ignore the sun, they ignore everything. They just model it as a system that is isolated in space. But we know that's not true.
But that's also natural first thing to try, right?
Oh, of course. It's the natural first thing to try, but at a certain point, it is not true because
Right.
Keplerian gravity assumes that your bodies are point masses. You
Mm.
know, you get to the name of
Hmm.
the article, beyond point masses. But also, you know, there's the sun, and the sun can affect the orbits of the TNBs, and there are lots of little effects.
Yep.
So this article is kind of the first venture into understanding if non-Keplerian effects are detectable at any level in
Cool.
TNB orbits.
Cool.
So the main source of non-Keplerian effects, uh, we think, and we show in this paper, is shape effects. So
Yeah.
TNOs are the individual components that make up TNBs are nowhere near spheres. We've done tons of studies that show that they're not spherical, they're not point masses. So there should be some sort of gravitational effect
Yep.
that influences the orbits.
Yep.
So that's what we dive into in this paper.
Cool.
So how we model TNBs that have shapes is we use gravitational harmonic expansions.
Okay.
So if you scroll down a little bit, we have the gravitational potential,
Yep.
the second order gravitational potential
Mhm.
of a body. And that basically parameterizes it as a triaxial body, which is the first kind of step out from spherical.
Yes.
So what we do is we characterize bodies based on their J2 and C22. So J2 is, I like saying, if you take a ball and you squish it to make it flat like a pancake, that's what J2 is. If you
Cool.
then take that pancake and squish it in another direction and
Yes.
make it kind of long like a sausage, that's
Hmm.
what C22 is.
Very good. Good.
So J2 is flat like a pancake, C22 is long like a sausage.
Good. Good.
So what we do in this paper is we model all of the bodies in terms of J2s and C22s.
Very good.
So
I'm with you.
the gravitational potential of a body, you also have to take into account that when you have a J2 and a C22, you have a body that's rotating. So if it's kind of a sausage shape
Yeah.
and it's rotating, say that the orbit period is much, much longer than the spin period of let's say the main body in the binary.
Okay.
C22 will actually average out most of the time.
Okay.
So if you have a body here and you have like a sausage shape here, I have a marker. You have a body here and it only moves, you know, a fraction of the orbit by the time it's gone from here all the way around.
Right.
C22 mostly averages out.
Okay.
So in most cases, C22 averages out. I did a whole project during my dissertation about when C22 averages out, when it doesn't. Basically, it doesn't average out when the spin period and the orbit period are about the same, or when you're at spin orbit resonances. So when they're commensurate. So if you spin twice for every one time you go around, or 3 times, or whatever.
Right. I mean,
C22 can become very important.
yes. Okay. Cool. I'm with you.
So we've been talking about non-Keplerian effects. So what a C22 and a J2 does, essentially, actually just focusing on the J2, is they cause slow precession of the apsidal and nodal, of the apsides and nodes.
Yes.
So generally, the period of this precession, it takes kind of on order of tens to hundreds of years for a TNB to fully precess. So that's when the periapse of the body can go all the way around in an eccentric orbit.
Yep.
So you have apsidal, which is the precession of the ellipse shape, and then you have nodal, which is precession of the inclination, essentially. And those have fairly similar rates. They're different by, you know, a few factors, and if the inclination is low,
you pick
they kind of average out to be,
yeah,
you know, a factor of a few off. But these rates are kind of tens to hundreds of years long in TNBs.
Okay, good. Thank you.
So just as a bit of an aside, I guess, J2, I say it's flat like a pancake, but when you look at all of the equations, the J2 is what characterizes the flat like a pancake. But similar to G and M, when you're calculating gravity, G and M always come together. They're never separated.
Yes. Yes.
Maybe in general relativity they are, or something like that. But in regular, Keplerian physics and all of that, G and M always come together. Similarly, J2 and R squared always come together. So
yes.
in essence,
yes.
You can't ever separate J2 and R squared. So when you are doing any Keplerian or non-Keplerian orbit fitting, rather, all you're measuring is J2R squared.
Yes.
You can never measure J2 independently without outside factors. So if you go and you have a complete shape model of a body, you can separate J2 and R squared. But TNOs are so far away that we know not very much about their shapes.
Okay.
So that does complicate some of the analysis a little bit. But if you assume some things, for example, here, I say, for example, assuming a homogeneous oblate ellipsoid with semi-axes, blah, blah, blah,
okay.
You can take a measured J2R squared value and infer some sort of shape. It's not a unique solution, but it is a solution. And a triaxial solution is, well, it's the first level that we go to.
Yes. Okay.
And it's probably a pretty good approximation for most objects. So if we can measure the J2R squared of something, or of a J2R squared from the orbit of a binary, we can actually learn things about the shapes of the binaries, of the objects that make up the binary themselves. So this is basically a way to get past telescope resolution, because the resolution, the angular diameter of the largest TNOs is small.
Yeah.
I think Pluto is the largest, and you can roughly get a map. I think they roughly got a map of it from HST.
Yes.
But smaller than Pluto, you just can't ever learn the shape, unless you wait 100 years until they have a 100-meter telescope or something like that. But we're really excited about non-Keplerian orbit fitting because it tells us about the shapes of TNO components, which have a lot of really interesting implications.
Yep, and that's a pretty mild assumption there. You got an oblate sphere.
Yeah, exactly.
It's pretty mild.
We make pretty mild assumptions, and then we learn a lot. So we're really, really happy.
Good.
So another thing to mention is that the shape determinations, or the shape constraints, I'll say, that we get out of non-Keplerian orbit fitting are actually kind of orthogonal to those you can get with light curve measurements or occultation measurements.
That's nice.
So there are some ways that you can learn the shapes of bodies, and this is kind of providing an orthogonal challenge or channel of information, which is really, really helpful.
Yeah.
We can also learn the spin poles. So the rotation poles of TNOs are basically completely unconstrained, except for a few cases that I cite. And occultations and light curves actually have a really hard time understanding the rotational poles of TNOs. But non-Keplerian orbit fitting is very good at finding the rotation poles.
Oh, yeah,
so we're really excited.
Yeah.
Another possibility is the fact that when we see these TNO binaries, there could be additional components in the system. And so when I say components, there could be other moons. So for a long time, we didn't know about the additional moons of Pluto. We only learned about them when we looked really, really hard with HST. So that could be another cause of non-Keplerian effects. And so in this paper, how we characterize those is basically the non-Keplerian effects from an unseen satellite are basically the same as having a very, very oblate shape. So if we measured the J2 of Gong Gong and its moon, if we measured J2, the J2R squared of Gong Gong, and it was way higher than we would ever expect, we could potentially infer
Yes.
that there's another moon in the system that could be causing those non-Keplerian effects. So in equations 4 and 5, I actually derived the effective J2 and C22 of a close-in satellite, where Q is the mass ratio, and A is the barycentric semi-major axis.
Cool.
Yes.
Good. Yes.
I actually did not clarify it closely enough in this paper, and I had to clarify it. I'm going to have to clarify it in a future paper that AS here is the barycentric semi-major axis. But
yes. Okay.
So not only are we sensitive to finding or learning about the shapes of TNO components, but we're also sensitive to learning about undetected moons around TNOs, which is really, really exciting.
Yes, very cool. So yeah, so deviations are either due to the shape of the body itself or some hidden companions.
Yes,
Nice.
and then there's kind of the meeting point of those two, where that we're really interested in, especially with TNOs, is characterizing contact binaries. So contact binaries are like is the exact meeting point between an unresolved component and a shape.
Yeah.
So we're also very sensitive to detecting contact binaries. And just as a spoiler, we think we've detected one. We'll get to it in
we will come back to
section 4 or 5. Yeah, we'll get back.
We'll come to that. Good.
So we'll skip through the next, I think the next section. Okay. It's basically non-Keplerian effects are detectable. Well, the paper shows that they're detectable. We expect them to be detectable too. But nobody's done it yet. So that's what we do.
Very good. There's a first.
So let's just jump straight into the methods, I think, because I think it makes more sense to do that. So what we do to do this non-Keplerian orbit fitting, I've talked so much about it so far. What we've done is we've written a package called Multimoon. So Multimoon is a Python-based Bayesian orbit fitting package specifically designed to complete Keplerian and non-Keplerian orbit fitting for TNBs. So publicly available on GitHub, anybody can go use it. I have put hundreds, if not thousands of hours into debugging it and making sure it's all great and all of that.
Wonderful, wonderful.
So for Keplerian orbit fitting, it just uses generic SpicyPy or Spice kernels.
Yes.
Which are super common across planetary science. So there's nothing really special in the Keplerian orbit fitting except kind of the Bayesian parameter inference that we've kind of tacked onto it.
Okay.
What's really special about Multimoon is its spin orbit integrator called Spinny. So Spinny can model the gravitation. So it can fully model the
cool.
N body, and we call it the N quadrupole problem. So it can integrate the translational and rotational equations of motion for an arbitrary number of interacting triaxial bodies.
Oh wow.
In theory, it's actually quite simple because it's just
integration,
gravity and torques.
Yeah.
In practice, it's a little bit more difficult.
Always.
And I will shout out our collaborator, Simon Porter, who actually wrote Spinny. He did a lot of legwork on writing Spinny, and we're really, really happy to incorporate it into Multimoon.
Good shout.
And then Multimoon also has various other kind of, when you're doing this orbit fitting problem, you have to account for, the change in viewing angle, the change in distance, the light travel time, blah, 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 which is done using kind of AstroPy related packages, things like that. And then at the heart of Multimoon is the Bayesian parameter inference, which is just done by MC, which I think probably many people who will be listening will know about MC. It's just a really simple Python-based MC ensemble sampler that can and have solved, hundreds of different problems. I think the papers have thousands of citations.
They do.
and they're great papers. So that's Multimoon. Multimoon is super great, and that's what we've used to kind of throw out the problem.
Very good.
So for the data we use,
Okay.
essentially the data is, well, we call it astrometry.
Yeah.
Astrometry is maybe a bit of a misnomer, because in essence it's relative. It's astrometry of the moon with reference to the brightest object in the system.
Okay.
So it's not absolute astrometry.
Okay. Relative.
And most of the data comes from images taken from the Hubble Space Telescope. So basically, we just take images at lots of times. We see the moon's here, the moon's here, the moon's here, the moon's here, the moon's here.
Yes.
And we kind of connect up the dots.
Yes.
So another collaborator, Will Grundy, he runs an online TNO database that basically publicly provides all of this relative astrometry for dozens of bodies. There's a gigantic amount of data on Will's website that has been completely transformative for our work.
Awesome.
So what we've done is we basically modeled every system in his database that we could, except two. I won't get into the reasons why. There are a few problems. But the data is fantastic data. So the relative precision on the relative astrometry is typically 10 milliarc seconds. So that's like of order a few hundred kilometers at 45 AU away. So we have super fantastic resolution from Hubble Space Telescope, and that kind of allows us to see these really minute deviations in the orbits of TNVs.
Cool.
So I think I'll skip through the rest of this. We do Keplerian orbit fits to kind of test how Multimoon does, and then we also do a set of non-Keplerian orbit fits.
Yes.
We make a bunch of assumptions that are important to state in the paper, but they're not super riveting discussion. And we use a bunch of settings, and
And Lord knows we only do riveting discussions.
Well.
Very good.
So in table 1, we just have basically the input parameters for all of the systems. So anybody can go and reproduce this work. Also, I will mention, if you go back up in the, or maybe down. So all of our inputs and outputs are saved on Zenodo. So if anybody wants to go check out our orbit fits or our non-Keplerian orbit fits, everything we've done, everything that's published in this paper are completely freely available under a Creative Commons license. So anybody can, if anybody's interested in tinkering with orbit fitting or anything like that, they can do everything that they want.
Love it. Open science.
Yeah, it's one of my big things. I love open science.
Yep.
So if we keep going down, we have a bunch of input parameters. It's not super riveting. And then in section 2.4, we talk. So I guess it kind of spoils the point a little bit. But we had crazy. Our results were better than we could have ever imagined, and we thought something was wrong.
Of course.
Good. So what we did is we checked everything, of course, and every time everything was correct. We couldn't figure out why we were getting these crazy results, other than we just had a good project. So what we did is we kind of relaxed all of the assumptions that we made in the kind of ensemble level analysis. We did very detailed fits for one binary in particular, Boric and Pabu. And so these are basically just talking about the assumptions we relaxed.
Nice. Good. I'm with you.
In section 2.5, we talk about fit quality. It's not super riveting discussion. We had long back and forths with the reviewer about fit quality. The fit quality is good. Let's just say that. We
Okay.
did. We're well above the state of the art, and you know, we have reduced chi-squared less than 1,
Yep.
RMS residuals less than 15 milliarc seconds.
Cool.
The weighted RMS residuals are less than 1.4. Blah blah blah. We have lots of. We've really robustly checked these because we were very concerned that something was going on.
But I want to be clear, it's because it was too good, right? Or
Yeah,
right. It
exactly.
wasn't because it was bad.
No. It was so good that we were worried that
Exactly.
something was going on. So in section 3 here, we basically just talk about the results of our Keplerian fits.
Mhm.
At the end of the paper, we have the orbit fits contained in a table in the appendix.
Yep.
We didn't want to interrupt the flow of the paper by
Good.
putting, you know, huge three-page
Table.
tables. And so most of the orbit fits were super great. We had a few, you know, hiccups that we talk about. And then in figure 1, if we scroll down,
Yeah.
we show an example of what the orbit fit looks like. So
Okay.
this is a corner plot.
Yeah.
I know corner plots are like the hot thing in astronomy, but for those of you who don't know, basically what we get out is a 1, 2, 3, 4, 5, 6, a 7-dimensional probability distribution, essentially,
Yes.
out of the orbit fitting problem. And I don't have 7-dimensional vision, nor does anybody else. So what we do is we look at the 2-dimensional probability distribution of each parameter pair. So that's what all of the kind of bullseyes are. And then at the top of the columns, we have marginal, so just 1-dimensional probability distributions of each parameter.
Cool. Okay. Yep.
And then the vertical and horizontal purple lines and the dots at the intersections of them are what the answers were on the online database that Will granted. So basically, we get these beautiful orbit fits that match almost exactly with the published results. And I love corner plots. You know, we super precisely determine all of the orbit parameters. We super precisely determine all of the correlations between the parameters. The one I like most is the semi-major axis mass one. I think it's at the top of this first column.
Yep.
You can tell that we actually don't super precisely measure the mass or the semi-major axis. What we're actually measuring is the orbit period.
Yeah.
So you have this line that's a line of constant orbit period, and you know, if you go a little bit too far out, you know, it doesn't match the astrometry. But if you go a little bit too far in, it also doesn't match the astrometry.
Yeah.
So I really like how we super precisely determine the period. I think it's just a cool illustration of, well, it's just Newton's laws, right? Or Newton's version of Kepler's.
Very cool. There we go.
So this is mostly an example. This is not super high level orbit fitting. And so if we go down in figure 2, we show how good the orbit fit was.
Residuals. Okay.
So pretty good residuals. The 2007 data point in orange is kind of 3 sigma off, which you know, is interesting. We wouldn't expect a 3 sigma off data point.
Yeah.
So that may hint at the future.
Oh, I see.
But we get pretty good residuals, and you know, we've made these plots for all of our fits. They're all available on Zenodo if you want to go look.
Cool.
And then next to that, in figure 3, what we do is we actually compare the Multimoon answers to the answers from the literature. So Z-score just compares those and basically just says how many sigma apart our answer is from the literature.
Wow.
And you can see that we basically just matched the literature. I mean, there are a few wiggles. You know, we have a few differences for certain parameters. You know, -4 sigma, +4 sigma. But you know, for an ensemble level analysis, it's fine. And we actually think that the likely reason that we get these 4 sigma residuals is purely because, well, I guess this is baked into the whole sigma thing. It says it's like, you know, we measure an eccentricity of 0.201 and with very small uncertainties, and the literature measures it at 0.199. And technically it's 4 sigma away, but realistically it doesn't really change the interpretation of the binary.
Yeah. And what is the, looks like there's a special black dotted curve here. What is this?
Yeah, so that's just purely a normal distribution.
Gotcha. Yeah. Okay. Just
So
for comparison. Okay.
yeah, just for comparison.
Gotcha.
So we can see that we do very well at reproducing the literature. So this basically reproduces 20 years of work.
Good.
And everything's good. We're glad that I know, reproducing past work never gets funded, never gets published. So we're glad to do that.
So important.
It is important. And we're happy because it confirms that Multimoon is doing that.
Right.
So then we can move on to the non-Keplerian.
Okay.
So basically what we did is, with the non-Keplerian orbit fits, is we compared, it's not chi-squared, although it's essentially chi-squared. We compare the likelihood from the Keplerian fit to the likelihood from the non-Keplerian fit. Okay. So and we make a ratio. So if the ratio is near 1, the likelihood of both of them are about the same. Yep. So that means that there's probably no non-Keplerian effects detected in the system. Yes. Because you can think about a Keplerian model and a non-Keplerian model as subsets. So the Keplerian model is actually a non-Keplerian model where you've put all of the Keplerian effects equal to 0, or the non-Keplerian effects equal to 0.
Yes.
So the Keplerian model is a subset of the non-Keplerian model. So we can do this likelihood ratio test, which makes our lives easy. Yeah. So likelihood ratio near 1 is, Keplerian is good, but a likelihood ratio much less than 1 means that there's something going on, that we've found some non-Keplerian effects. So the whole goal of the paper was to kind of identify where to focus our attention. Yes. Non-Keplerian fitting is an order of magnitude, or maybe even 2 orders of magnitude, more difficult than Keplerian orbit fitting. So what we've really done is we've done kind of short, abbreviated non-Keplerian orbit fits to see where we can focus our attention. So here we put a cutoff if the likelihood ratio is less than 0.1. It's something to look into.
Flag it. Yep.
Yeah. So if you scroll down in figure 4, we basically plot all of the likelihood ratios as a function of the best fit J2. And so just as a reminder, J2 is flat like a pancake. And you can see that we have some very, very small likelihood ratios.
Wow.
So for some objects like Salacia, Orcus, Gong, we have very, very significant improvements in fit quality when we use a non-Keplerian orbit model.
Oh wow, indeed.
And that makes sense. Salacia, it's been noticed in the literature that its orbit is like 3.7 sig. I think it's 3.7 sigma, inconsistent with a Keplerian orbit. So that's good to reproduce that we find a strongly non-Keplerian orbit. But we also see various other systems that we didn't expect. So Boric and Pabu, it's just a regular, it's not a particularly interesting binary, but you can see that it has a much better fit quality, at least as measured by the likelihood ratio, when using a non-Keplerian orbit.
Interesting.
And so up here at the top, you can also see that there's lots of systems that, likely are just totally Keplerian. Either they're too far separated to detect non-Keplerian effects. Right. The astrometry is not good enough.
Fair enough.
There's not enough astrometry. there's not enough time, like the astrometry hasn't been taken over a long enough time.
Okay.
So there's lots of effects that, would make the orbits probably just Keplerian.
Oh.
And so we were really, really, really excited about this result. And one thing that we noticed is that that the likelihood ratio was actually kind of, it was at least a little bit roughly correlated with radius of the central body in the binary.
I was going to say there's a trend there. We can call it
wrong. I don't know if I would call it correlation, but there's a trend.
Yeah.
And that's likely because the larger binaries, so Salacia, Orcus, these are kind of the dwarf planet type TNOs. So they've just been observed more because they're cooler and more interesting. They also have tighter orbits, which increases the detectability of non-Keplerian effects. Yeah. You had a question?
Yeah, some of these are marked with asterisks and others are not. What is that?
Yes. So when we do orbit fitting, there's a problem with if you don't observe over a long enough time period, you can't tell. There's something called the mirror ambiguity, and basically, here I have my engineering.
Yeah. This way or this way.
Yeah, so you can see that it's orbiting this way, but you don't know if the orbit is oriented like this or like this.
Right.
Because we can't tell when something's coming closer to it, when one object is coming closer.
So prograde, prograde.
Yes, essentially. Okay. So for some of these objects that we studied, that mirror ambiguity hasn't been broken yet. So the star, so the asterisk is prograde. 2 asterisks is retrograde.
Retro. Okay.
Yeah.
Very good. I'm with you. Okay.
So we were really excited. We were expecting to say, oh, there's something slightly detectable in 2 objects, but there are actually 8 objects below our threshold.
Yeah.
And there are a ton of objects that are just above our threshold.
Yeah. Which was an arbitrary number.
Yeah, I mean, the threshold was chosen to be, not conservative, but not too,
aggressive.
So, it was just kind of something generic.
But it is there's a bunch right around your chosen threshold.
Yeah, exactly. So we later in the paper talk about how we need observations to look at some of these. And, of course, observations of the ones near here at the bottom would be great.
Yeah.
But we're actually almost more interested in observations that are kind of between 0.1 and 0.2 likelihood ratios to kind of see if those, maybe it's just, random error that they're, random chance that they're there. Or, we would like to see kind of a splitting of that.
Right. Something physical there.
Yeah. So we were really excited about these results. And in table A2, we have all of the best fit models published, which is really, really fantastic. One thing we have to worry about with figure 5.
Oh, sorry.
You're good.
Slide down to table 2 here for a second.
Yeah, A2, I said, sorry. In the appendix.
Oh, I'm sorry. Yes, that's
yeah.
Oh, my bad. Okay, so let's go back up to figure 5. My bad. Sorry.
So in figure 5, one thing we were particularly worried about is that the orbits that you get when you use a Keplerian analysis are wrong because of non-Keplerian effects. So what we do here is we compare our Keplerian analysis to our non-Keplerian analysis.
Yes.
And we see that for the orbit orientation angles, so in brown and purple, we know those angles precess in a non-Keplerian case. So it's not unusual that we would get different answers in our Keplerian versus non-Keplerian. But thankfully, the mass, the semi-major axis, the eccentricity, the inclination are not overly affected from this non-Keplerian analysis. So everybody can still keep using Keplerian analysis. I mean, we think you can probably do better, but it's not the end of the world.
Right. And these 2 omegas were equation 2 and 3 respectively as we went through on J2.
Yes.
Yep.
Yes. So not unusual that those change.
Yeah, I wouldn't expect those to be a little different then. Okay, good.
So here now in section 4.1, we actually go through and I kind of do a short description of each of the objects that we have detected non-Keplerian effects. And we have lots of things, and we say everybody needs to go out and observe these bodies.
Indeed.
We find a few interesting things. Nothing that's like completely earth-shattering. We find that dwarf planet kind of bodies tend to be a little bit oblate, like you would expect.
Yeah. Okay.
We see smaller bodies have larger J2s. Smaller bodies have larger J2s.
Yep.
Because when you're a smaller body, you're less spherical.
Yeah.
Larger bodies have smaller J2s. We basically find everything we expect, but we find so much of it. So we're really excited, and I guess for time we can slide down to. I will say in 4.14. We do explicitly mention Boric and Pabu, which we then talk about in section 5.
Okay.
So if you want, we can just jump straight to there.
Okay, I just get a handle on some of these. We'll talk about the future here in a bit. And section 5. Okay.
So what we wanted to do is we wanted to take one of these small binaries that we didn't expect to have non-Keplerian effects and do a really, really detailed analysis. So what we did is we threw probably several CPU years at understanding the orbit, which, sometimes I question if it was a waste of time, but we found really, really great things. So we were really excited about it.
Not a waste of time.
No, probably not. So, we confirm that kind of relaxing some of those assumptions doesn't necessarily change things. We find a similar likelihood ratio in our kind of full-on testing that we did in our original tests.
Right.
We in this one we actually explicitly model C22 as well. In the first one, we just kind of said, let's not worry about C22. Sure. But now we explicitly model C22.
Okay.
And in the end, we find kind of a 3% probability that random chance would produce an orbit fit there's a 3% chance that the Keplerian orbit fit is the right model.
Yes. Okay.
So we find, it's kind of 2-ish sigma result that Boric and Pabu have a detectably non-Keplerian.
Nice.
And then we did lots of tests to kind of fiddle with input parameters to really, really make sure that things were great. But if we look at this table, the thing I'm most excited about here is, we measure all of these things, but the primary zonal gravitational harmonic, so J2, we measure it to be about 0.445.
Wow.
Which is significantly non-spherical. So I think I did a calculation that Arakoth, so we all know the shape of Arakoth, it's like this little snowman thing.
Yes.
Has a J2, I think it's about 0.35.
Yes.
So it's potentially even more elongated, potentially more weird than Arakoth.
Sausage.
Yeah. One thing we compare it to is an asteroid called Cleopatra. That's it's kind of dog bone shaped. It's this really, really long body that's kind of fat at the ends, and we think that Boric must be somewhat similar to that.
Yeah, very cool.
And you will see that I say that we've measured J2, even though I said we only ever measure J2 r squared. We make some simple assumptions about the size that are kind of reasonably well justified to get to a J2, so we can actually interpret it. There is some uncertainty there. And there is some uncertainty. We only modeled the J2 of Boric, not of Pabu. But even given reasonable parameters, you still get that the J2 of both bodies have to be about the same to basically Pabu's J2 doesn't really matter.
Very cool.
So we think we found a contact binary, with a moon, which is
Oh,
very, very fun.
wow. That's great.
We can also measure the obliquity of the moon in relation to Borosi's equator. So that's primary obliquity with respect to the mutual orbit. So we think that if this is Borosithi and its contact binary, the orbit is 45 degrees offset.
Wow. 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 Okay.
Which is pretty cool.
Yeah.
Unfortunately, we can't tell if it's we actually can't tell if it's if Borosithi is orbiting in the same way that, or sorry, if Pabu is orbiting in the same way that Borosithi spins. So we can't tell if it's prograde or retrograde. So in here, we actually only explore the retrograde solution, but it's 45 degrees in the other way, but orbiting backwards.
Yep. Yep. I'm with you.
Wow. So we're fantastically excited about this.
Yes.
And we think that it implies that Borosithi is a contact binary.
Oh, very nice. Congratulations.
One alternative explanation that I kind of hinted at the beginning is, well, we find this really, really large J2. Could that actually be another moon? So we did a bit of an analysis of, trying to figure out if the J2 could be from another moon, and I think it's in figure 8.
Okay. Figure 8, 7, and 8. Okay.
And we basically calculate, given a mass ratio here on the bottom on the x-axis, what separation would that putative moon have to reproduce the J2 that we determine in our orbit fits. And we see that it's it's somewhat reasonable. They're separated by a few hundred kilometers. And we actually plot two close binaries. So 2014 WC510 and 2011 JY31 are just two close binaries that we think are kind of decent analogs. And then Lempo and Hiisi is actually a triple system. So it's a central binary orbited by another moon. And it's a hierarchical triple.
Yep.
And that's not quite the same. We're seeing a binary that has to be somewhat more compact in the center. And we think the best explanation is actually not that it's a binary at the center, it's a contact binary at the center.
Cool.
And it's not in this paper, but I'm really excited. We've actually come up with a name for it, because we kind of like referring to them as triple systems because it's a contact binary with a moon. But triple systems are not contact binaries with a moon. So we've started calling them contact hierarchical triples.
Cool. That's a mouthful.
Yeah, it's a bit of a mouthful, but I think it's a good way to kind of to differentiate these. And there's actually, a few years ago, there was a paper published that suggested that this similar setup where you have a contact binary surrounded by a moon, there's another one of them. It's called Monway and Tharandor.
Okay.
And that's been proposed to explain kind of some light curve observations. So we're very excited about this. I hesitate to call it detection, possible detection of a contact binary among the TNO population, or the TNB population.
TNB population, yeah, very good.
Which is important and exciting. It's really exciting because some of the simulations about how these TNBs form actually predict the existence of hierarchical triple systems and elongated bodies at the center of these binaries. So we actually think that this is indication that formation models and our observations are kind of converging upon one another, which is great.
Very nice.
Moving back, we can look at the orbit fit in figure 6. So for those of you who are diehard corner plot lovers, we have a really beautiful corner plot here.
Okay,
Uh,
even more. There we go.
yeah, it's a little bit unwieldy once you get to so many parameters.
7, 8,
Um,
12, 13.
yeah, so we do a lot of stuff here, and we fully measure all of the parameter degeneracies. We do our due diligence on getting the orbit fit.
A little bit wider spread on
Hmm.
A as opposed to when we saw the first corner plot. It was a really sharp line. Here's we're a little
Yeah,
bit down.
yeah, and that's actually another effect of non-Keplerian orbits is that it doesn't just process the apses and nodes. It
Oh,
actually also modifies Newton's version of Kepler's third law. So it actually modifies the mean motion slightly.
yes.
So before we had this very, very tight correlation between M and A when we measured the period, but now it's not as tight a correlation. It's not as thick because J2 kind of can modulate some of that and absorb some of that period,
Yeah, so to
which
speak.
is a very, very cool,
And
it's a very, very cool kind of confirmation of just analytical theory.
yes, yes, yes. Very nice.
So we're fantastically excited about our results. And so we have an ongoing, I think it was cycle 30 on HST. We had a program ongoing. It was supposed to have finished by now, but it's still ongoing to observe some of these binaries.
Okay.
And
Okay.
one of the things we did in preparation for that is kind of understand when to observe next.
Yes.
So in figure 9, actually, if you go a little bit past figure 9,
Okay.
what we've done is we've come up with this quantity which we call information gain.
Cool.
And so basically what we can do is we can take all of these orbit solutions that we have in our corner plots,
Yes.
kind of predict them forward, push them forward, and find how big the cloud of predicted positions is
Yes.
at a certain time.
Yes.
Um, Divide that by like the typical uncertainty that you can achieve with Hubble.
Okay.
And
Okay.
we get what we call information gain. So it's basically, I if I
I like it.
it is the equivalent to calculating the average expected
Yes.
square root of the chi-squared of
Yes.
a new relative astrometry observation. So if we plot that over time, in figure 9, we
Cool.
see
Ooh,
uh,
here's
we
our
see information gain in gray. So we see that the
okay.
information gain observed at a bad time, so at the dips,
Yes.
is almost half of the information that we can get by observing at a optimal time.
Very cool.
So we've actually had great success with using this to kind of motivate very, very precise targeted observations with HST. Um, saying and if we get good observations at a certain time, we can get so much better constraints. And then I also plot separation here because they're slightly correlated with each
Yeah,
other.
I was going to say you're getting the most information out when they're relatively closer.
Yes, and that's because we can't, when they're close, we don't observe. So the greatest uncertainty in the position is when they're close together because we've never been able to observe when they're close together before.
Got it.
So there is some, it's not quite as exciting as you want it to be, but
Pretty good.
if you play this game of how close can I get it to, optimizing information gain while still maintaining observability, you can kind of play some games and get really good observations, which we're really excited.
Very cool.
And that's kind of it.
Cool.
I will acknowledge we have an appendix where we do some other Keplerian fitting with constant offsets. It was a whole journey that just took away from the main point of the paper that we wanted to publish somewhere that is interesting if you're an orbit fitting junkie. And then we have tables of orbit fits. So these are publicly available again on Zenodo. So anybody can go and take these orbit fits to do whatever they want with. And we're really, really happy to reproduce the past literature and kind of take us to the next step.
It's the next level. That is
Yeah.
so awesome. That is so awesome. Very cool. Simon Porter. Oh yeah. Very nice. Ben, I want to thank you so much for walking us through your very beautiful article. Very nice.
Thank you. Thank you.
Great. And you kind of hinted on it there a little bit at various points as we were going through. So let me go ahead and push on a little bit.
Mhm.
And where do you think we go from here, given the published article? I mean, in some sense, it's in the title. There's a 2, so one could ask, is there a 3? Is there a 4? But you also hinted several times as we went through that there were new observations. There will be new stuff coming. So next steps.
Yeah. So I will give a plug. There is a 3. There is a 3 published in PSJ. There's a 4 published on Archive, which hopefully should be in PSJ soon. I'm not in charge of that one, so it'll happen. But if you want to read the preprint, you can go read the preprint.
Good.
And so 3 was doing the same thing for the Haumea system. So Haumea is this oblate object that has a super high J2. It's really big. It has 2 moons. It's complicated dynamically. So we do the same thing for Haumea in paper 3. And then in paper 4, another one of the objects that we kind of learned about in this paper was Altura. And we kind of take it and run on that one in paper 4. We have an ongoing HST program right now to look at 4 of the kind of surprise binaries that we found, and several proposed HST programs going. Hopefully, if you're a reviewer, please review us nicely. So that's kind of observations wise. I think everybody should go observe these objects. But kind of science wise, I think this paper has just kind of opened this whole new subfield. I don't know, it's not necessarily a subfield, but it's kind of opened up this whole landscape of everybody can go do this non-Keplerian orbit fitting of any TNO binaries, and I think there's plenty out there to discover. You just need computer time, I guess.
Go look.
Yeah, go look. Very cool. And if you are somebody who's interested in Multimoon and wants to collaborate, if you're interested in any of the objects, come talk to us. We have more to do than we have time. So
there you go.
If you want to take it and run, talk to us and we'll help you get started.
Very cool. Great. Very good. Very good. Ben, that was awesome. I want to thank you so much again for walking us through your very life. Thanks.
Thank you.
And that will do, everyone. And I hope this made your astronomy day just a little bit better, and we will see you on the next one. Bye-bye.
Bye.